So we're working on question 3.3, number 12. We've got this function f of x, right now, f of x equals x plus 6 over x. And I just want to point a couple of things out. One is in terms of the domain, x can't equal 0, right? Because we've got an x in the denominator. So just keep that in mind. X can't equal 0. Otherwise, all real numbers are fine. Just anything but 0 is in the domain. So as we go through, like when we're looking for, a max or a min or an inflection point or anything like that, it can't exist where x equals 0 because that's not defined for the function. Another thing I want to point out, because this might come in handy later on, is we could also rewrite this function if we think of x as being equivalent to x squared over x, right? That's the same thing as x. If I simplify x squared over x, I get x. So if I think of it as x squared over x plus 6 over x, I could rewrite this as x squared plus 6 over x. That's another equivalent version of the function, so just want to keep that in mind. Okay, so the first couple questions are going to ask us are about increasing or decreasing areas of the function and whether there's relative extrema. So for both of those, I'm going to start off using the first derivative test. First derivative test. All right, so for the first derivative test, obviously we need the first derivative, f prime of x. If we look at f of x, actually let me write a third version of f of x. We could write it as x plus 6 times x to the negative 1 power. So that's going to come in handy for our first derivative. We could calculate our first derivative as 1. Derivative of x is 1. And then minus 6x to the power negative 2. We could also write this as 1 minus 6 over x squared. All right, so both are fine. So for our first derivative test, if we're looking for extrema and we're looking for where the function is increasing and decreasing, we want those critical x values. So these occur where either the first derivative equals 0 or where the first derivative does not exist. F prime of x, I'm just using DNE for does not exist, where x equals 0, right? And we know that. That's a domain issue that we've already established. So function, or the first derivative of the function doesn't exist at x equals 0. And then we can also try setting f prime equal to 0. So if we do that, if we set this puppy equal to 0, I could add 6 over x squared to both sides and get 1 equals 6 over x squared, multiply both sides by x squared to get x squared equals 6. And then I can take the square root of both sides, but I want to remember my square root property. Taking the square root of both sides, I get x equals positive or negative square root of 6. So my other critical values are going to be x equals positive or negative square root of 6, and that's roughly equal to plus or minus 2.45 if you put that into your calculator. Alright, so these are our critical x values. Okay, so now we're going to create our little line graph. And we've got 0, we've got, I'm going to call it negative 2.45, standing in for negative square root of 6, and positive 2.45, standing in for positive square root of 6. Alright, so we're going to evaluate the first derivative at values in these different intervals and see what's going on with our graph. F prime of, let's say, negative 3. Would equal 1 minus 6 over negative 3 in parentheses squared, which would be positive 9. 1 minus 2/3 is going to be greater than 0. So we have a positive first derivative there. Alright, f prime of, let's say, -1. -1 in this interval. That's going to be 1 minus 6 over 1 squared, which is just 1 minus 6. It's going to be negative. So negative first derivative there. If you go through and do the same for these other two, if I do f prime of +1, you get 1 minus 6 again. That's still going to be less than 0. Negative. And finally over here, if we do f prime of +3, for example, we'll get the same result we got on the far left. We'll have 1 minus 6 over 9, which is going to be positive. Okay, cool. So if I were to draw a sketch, a very, very rough sketch, obviously, of what's going on in this function, it's increasing here, and then decreasing here, continuing to decrease here, and then going back to increasing up here. Alright, so let's pull all of this together. And by the way, remember that our function does not exist at x equals 0, so we'll keep that in mind. Alright, two things we're trying to answer here with the first derivative test. First thing is where the function is increasing and decreasing. Function is increasing from -infinity to negative square root of 6, and it's also increasing square root of 6 up to infinity. And then the function is decreasing wherever I see those negative signs. Now, if the function existed at 0, I could just say it's from negative square root of 6 to positive square root of 6. But because we have that gap where x can't equal 0, I have to put negative square root of 6 to 0, and then 0 to positive square root of 6. Okay, so there's one part out of the way. And then in terms of our relative extrema, let's change colors here so this doesn't get too crowded. If you look at this super lovely sketch that I've drawn you guys, we can see there's a max up here and then a minimum value up here. So we've got a relative maximum where x equals negative square root of 6, and we've got a relative minimum where x equals positive square root of 6. So I want to evaluate our function, because my lab math is going to want the exact values. I'll evaluate my function at f of square root of 6. And you can use whichever of these versions of the function you want. For example, over here, I'm evaluating f of square root of 6 using this guy. That's square root of 6 plus 6 over the square root of 6. Well, up in the numerator where it says 6, that's the same thing as square root of 6 times itself, right? Square root of 6 times square root of 6. Cancel one of those square root of 6's out. So I end up with square root of 6 plus square root of 6. There are little coefficients of 1 out front for a grand total of 2 square roots of 6. So that minimum point, I'm going to put relative minimum is at the ordered pair square root of 6 and 2 square root of 6. Alright, and if you do the same kind of process, I'm just going to pick another weird color. If you do the same type of process and evaluate f of negative square root of 6, following the same process, you should get that that's equal to negative 2 square root of 6. So that means we've got our relative max at negative square root of 6, negative 2 square root of 6. Okay, so those are the first two parts. We've got where our function is increasing and decreasing.